Hello everyone. So in today's video, I am going to discuss some important models from the chapter electrostatics in the book Pathfinder. So along with solving some standard models and important questions, I am also going to teach one very important concept called reduced mass system, so which can be very helpful in solving questions either it is in mechanics chapter or gravitation chapter or electrostatics chapter, even in some of the good questions in atomic physics also we can use this concept, reduced mass concept, which is very important. So obviously, like, many of the students will be having confusion regarding this, or they don't know how to use it, so or else they don't even know what is a reduced mass. Okay, so in this video, so it's a beautiful concept, so which obviously gives some positive edge over the others in solving the questions in better way and easiest way. So that might be in electrostatics chapter, or as I said, it can be in electrostatics chapter or mechanics or gravitation or like wherever. So like by knowing this chapter, obviously you can solve the questions in a better way and easiest like way. So anyway, you'll understand in this video. I'll teach the concept. Along with that, I'll take up two questions based on simple questions on reduced mass, just to make you understand what is reduced mass, when to use and how to use, and how the question becomes so easy after using that concept. So all those things we are going to see in this video. Okay, then, so let us jump into this today's class. So in this question, in this first question, they are telling, for a cube of uniform charge density rho, length a. So length is also given as what? Length is given as a, and they're telling that its potential at the corner is what? V naught. Length a is given. Potential at the corner is V naught. Let's say for this uniform charge density is rho, side length is a, and they're telling that potential at the corner is what? V naught. Now they're telling, if a cube of side length a by 2 like this, if a cube of side length a by 2, let's say this cube is removed, which is having a side length of what? A by 2. So after removing, now they are asking what is the new potential at this corner point P. Okay, let's say this is corner point P. Now you guys need to tell what will be the potential at the corner point P. So this length is A by 2, the side length with which the side is removed, and basically this side length of the cube is what? A. So, sir, how to approach these type of questions? The same thing can be asked for electric field as well. Okay, the same model, but I am sticking to electric potential here. Yeah, but same concept whatever I am telling you can also apply for electric field as well. So here the key concept that I am going to use is what, sir? Is dimension analysis. Dimension analysis. Okay, this comes very handy in some very important chapters. Okay, instead of solving the questions directly when we don't know the formulas, then this dimension analysis or symmetry. Okay, dimension analysis plus symmetry is also required over here, plus symmetry. These two things are going to help in solving this question. So let us see how these two things are going to help in solving this question. First of all, we know formula for potential for due to some standard objects, right? What are the standard objects? It might be like a point charge. Then we have seen the formula for, like, you will be seeing the formula for ring, disc, rod, and solid sphere or cylinder or sheet, all these things, right? Potential difference, all that stuff. But the formula of electric potential due to a solid cube or like cuboid, all these things are not standard, right? Or a plate, like a triangular plate or like square plate, all these things are not standard ones, right? But one thing you need to understand, the dimensions of like in all the formulas, if you just go through that, the dimensions will be something like this. K is some constant, okay, in which not only 1 by 4 pi epsilon naught can be there, any multiple can be there, and along with that charge will be there, and denominator will be having a length term, right? So general formula for point charge is what? Kq by r. You can see some constant multiplied by charge divided by what? The distance where you need to find. So like similarly, so here you can say potential due to the cube at the corner can be given as, I don't know the formula, okay, but I can give, like I can design a formula based on what dimension analysis, that is I'm telling some constant k is there, okay, not like again if I write k you might be confused with 1 by 4 pi epsilon naught. So let's say some constant c is there, c into q by the dimension of the cube a, the dimension of the cube a. If let's say we want to find electric field, instead of like a, then you will be having what, a square, because you know the formula of like electric field you will be having r square term, right, length square term in the denominator. So this is the formula for potential due to a cube at the corner of what, at the corner, so which is given by v equal to c into q by a, where q is the charge, right, total charge. So you know the total charge can be written as what, so therefore v can be written as c into, the q can be written as rho into what, a cube by a. That means you need to understand that potential is directly proportional to what, a square. That means you guys need to understand that the potential is directly proportional to what, a square. Now okay, so let us keep this formula aside, but now our task is to find potential due to this cube, okay, in which some part is removed. Now we need to find this, right? So it is a pretty much very standard concept in like rotational dynamics, center of mass, all these chapters in mechanics, in gravitation, in electrostatics, in magnetism, all these things. Whenever remember some part is removed, okay, some part is removed, then you need to understand here. I am writing one more concept. These are the concepts that are required to solve this question. Let me change this color so that you understand. Yeah, plus I need one more concept here. Whenever removal of mass is there, okay, whenever removal of mass is there from a known shape or the symmetrical shape, if they are removing something and they're asking us to find something, right, then remember you're going to use one more concept called filling and defilling. Filling and defilling. So these are the concepts that are required to solve this question, that is dimension analysis, symmetry, and also filling and defilling. So when filling and defilling is like required, as I said, from any known standard shape, if they're removing some again the known shape, okay, or the symmetrical, in a symmetrical manner, then we'll use a concept of superposition, that is we'll fill it and we'll find due to the total figure, and then subtract due to like what, whatever the thing that we have added, that means defill it. So fill and defilling. So by doing filling, what we are doing, we are converting that into like what, a known system, okay, known, like known figure for which we know the formula, and then whatever the figure, like whatever the thing that we fill, that is also a known thing. So due to that also we know the result. So we'll do that, the like result due to the filled part minus result due to the removed part, you are going to get the answer for whatever the required given condition is there, right? So that means by using that concept here, by using this concept over here, let's say like as I said, filling and defilling, right? So after filling it, I know the potential at the center, like the potential at the corner will be this one, right? So for the full cube, already I know the potential for full cube. For full cube, v equal to what, 0 a square. Then for half cube, for like not, you can't say it's like half cube, for the removed cube I will say, for the removed cube which is having side length what, a, then you need to understand v dash. Let's say that potential is what, v dash, which is equal to, c is a constant, rho is a constant, has the same charge density, but the side length is what, a by 2. That means, so therefore from here we got a result that the potential v dash, potential due to that small cube of side length a by 2 at the corner will become how much? Will become, so you guys can see that c rho a square by 2, right? But c rho a square is nothing but v, okay, so which is given as v naught, right? So let me call it as v naught. So therefore what is the value you are getting? V naught by 4. V naught by 4. Now as I said, so filling and defilling, right? So when you want to find the potential due to this removed part, so after filling it, I found what is the potential to the entire thing, and then also I know the potential due to the removed part. So therefore potential due to the required part. Therefore, what is the result? Therefore, final result is potential due to the given situation would be, as I said, by using superposition theorem. First we have filled it, so and we will find the potential due to the entire thing minus potential due to the removed part. So therefore potential due to the given situation equal to V naught, which is due to the full figure, minus what? Minus V dash, right? So because of full figure I know that which is nothing but V naught, and because of the removed part I got it as V naught by 4. So therefore V naught minus V dash is nothing but V naught by 4. So the answer would be what? 3 V naught by 4. The answer would be what? 3 V naught by 4, right? So I hope this is pretty much clear for you. On the similar model, I'm going to discuss one more question here. Okay, so what is the question? See, so they were telling that for a cube of uniform density rho and charge length a. So here they're telling is given potential at the center is what? V naught. So they're telling the potential at the center is V naught. Now they're asking. What is the potential? Yes, one second. Find the potential at the corner of the cube, right? Okay, yeah. So basically they have given the potential at the center, and now they're asking what's the potential at the corner, right? So let's say this center, let me take this center as, let's say, C. Originally, let's say length is given as what? A. Original length is given as A. Now by using this the previous concepts that I've told, you guys can write the potential at the center by using the formula. Okay, so some C will be there. Okay, not the previous C, so it can be a different C as well. Some C into rho into A square. So this will be the potential at the center, right? This will be the potential at the center. But now our task is to find the potential at the corner, right? Any corner, all the corners will be symmetrical with respect to this one. So to do so, what I am doing, so let's say I want to find the potential at this corner. Which corner? Let's say I am calling this point to be what? P. Let's say I wanted to find potential at P. Already I know what is the potential at the center. I need to find the potential at corner. So now what I am doing, I am constructing an like cube, okay, which is of side length 2a, such that this cube of side length a will be one of the 8 cubes that is required to build a cube of side length what? 2a. Actually, to build a cube of side length 2a, we can use 8 cubes of side length a. So like by considering this type of cubes, let's say there are like 7 more cubes are there. By using all these 8 cubes, I can build a room like this, right? I can build a box like this. Now basically I need to find what is the potential at the corner, right? Potential at the corner. But already I know the potential at the center, right? Potential at the center already I know. By using this formula, I'll try to find what's the potential at the corner. Now here you need to understand the following points. You need to understand here how many cubes are there. Total 8 such cubes are required. Total 8 such cubes are required to get, total 8 such cubes are required to get a what? Cube of side length 2a. So we got 8 cubes, and the next important point is for all the 8 cubes, the point P is symmetrical. That's how I constructed. No? Already I told you I'll be using dimension analysis, symmetry, and filling and defilling. So as I said, I have constructed figure in such a way that the point P would become what? The symmetrical point for all the cubes. Now P is the corner point for the given cube. P is the corner point for the given cube, but it is common and symmetrical. It is common and symmetrical for the new system. And you need to understand that for new system the point P is nothing but what? For the new system the point P is center point. For the new system the point P is what? Also it is a center point. Also it is at center. As I said, it is a symmetrical point. As I already said, it's a symmetrical point. So whatever the potential that is there because of one cube, okay, let's say imagine that potential due to one cube at the corner is V dash, let me call it as potential due to one cube at the corner be what? Corner be V dash, at the corner be V dash. Now our target is to find V dash only. They are asking what's the potential at the corner and they give the potential at the center. Now I need to find the V dash. Sir, how to find this V dash value means, now when the side length is double, so therefore let me find the new potential at the center. What I will find? New potential at the center. Let me find new potential at the center. New potential V new. Sir, how to find V new? So C is same, rho is same, constant. But now the side length is what? 2a whole square, which is nothing but new potential has become what? 4V. New potential should become what? New potential should become 4V. Okay, sir, we understood the new potential for the entire system at the center is what? At the center should be 4V. Because the side length has become double, as V is directly proportional to a square, so the potential become 4V. But you need to understand this 4V potential is because of what? The 4V potential at the center is because of 8 such cubes, right? 8 similar cubes of whatever the dimensions that we required. So therefore, so that means, but we know V new we can get it from where? 8 such cubes are there, right? 8 into potential due to each cube, already I consider it as what? V dash. Already I consider it as what? V dash. So therefore, if you just substitute there, V dash will become what? V dash will become, V new is 4V, so 4V by 8 will be equal to how much? It will be equal to V by 2. It will be equal to V by 2. So this is the potential. When potential at the center is given as V, potential at the corner would become what? Potential at the corner would become V by 2. So I hope it is clear. Okay, so this is very important model where dimension analysis is used, symmetry is used, and the filling defilling part is also used, right? So with the help of all these concepts, okay, so is able to cover, like we are able to tackle this question. Similar way they can also ask for the electric field as well. Okay, so yeah, so next let us move on to the a different model. So here they are telling that there are two charges. Like here one charge is fixed, which is having charge q and mass m. Another charge is free to move. Okay, and which is at a distance d, like the distance between these two parallel lines, the line of motion of this one and this particle, the distance between these parallel lines is given as what? T. And initially they are telling that it's at very far. Okay, it's like very far from this charge. That means indirectly you can consider it as at what? Infinite distance. Now the question is, they will be asking you to find the closest approach. The question will be find the closest approach. Sir, how to find the closest approach? See, you need to understand. Let's say I'll draw the diagram for this situation at some time t. Sir, what will happen basically here? It wanted to move in this way, but as this is fixed, okay, it's not going to move anywhere. We know the electrostatic force or the Coulombic force will be along line joining what? Along line joining both the particles. Okay, the Coulombing force will be like what, sir? Along the line joining both the particles. So then you need to understand that. So the path would be something like this. Here the fixed Q and M is there. Let's say it started over here. Then the path it would be following will be something like this, right? It will be repelled. It will be repelled like this. Let me change the ink. It will be repelled. And sir, when the like approach should be like closest, obviously the approach should be closest when there is no relative velocity of approach, right? When there is no relative velocity of approach. So I'm just showing you two different points. Let's say in this point, the like let's say charge is over here, then velocity will be obviously tangential, and this is the force line of action between the two charges. So you can see that when theta is like let's say acute, then we'll say it is what, it is trying to approach towards this, and I'm trying to draw three different cases. Okay, this is another case where the velocity is tangential, and angle between them is what, 90 degrees. So this is one case is acute angle, another case is 90 degrees, and another case is, let's say I'm taking this part over here where the tangent can be drawn like this, and angle between them is like what, theta, which is obtuse. This is acute angle, and this is 90 degrees, and this is what, obtuse angle. Total three like different cases that I have shown in this entire path. So in these three cases, what will happen, so in this case, so this will be like what, sir, separated. This is the thing that we will be using for what, separation, because we will be having velocity of separation, right? So here in this case, no velocity of approach or no velocity of separation, but in this case we will be having a component towards this charge, right? So because of that we will be having approach. In this case we will be having what, approach. So that means initially you can understand that from here to here the particle will try to approach towards Q, and from here it will try to separate from the Q. Okay, from here to here it will try to approach the what, approach the charge Q, and from there it will try to what, it will try to go separate from this charge. That means obviously the closest approach should be what, initially I am telling that I am trying to approach towards the charge, so the distance will be decreased, because at any instant there will be a component in the direction of the charge. That means that's called as relative velocity of approach. Because of the relative velocity of approach, the distance is what, becoming like less and less, right? So that means it is approaching, so the distance will become smaller and smaller. So, and after a certain time when the angle becomes 90, after that the angle will keep on increasing. If the angle increases, then it becomes obtuse angle. When it becomes obtuse angle, that means then you are going to get what, velocity of separation, right? Then you are going to get what, velocity of separation. So where the separation starts increasing. So therefore obviously the minimum distance you are going to get in the transition time of what, in the transition time of approach to what, approach to separation. That means during the time when it is changing from the state of being approach to separation, in between you are going to get a point where the separation between them will be minimum. So that is only called as what, the distance of closest approach. Let me say at that instant the velocity will be what, v. So that means here I have two unknowns. I need to find the what, r minimum, and I got some another unknown what, I got another unknown v. So we have two unknowns and my target is to find r minimum. Sir, how to approach this question? See, one very very important thing here is, we know whenever 2 point charges are there, okay, force will be always like passing through those 2 points, right? Point charges, it might be attraction or repulsion, irrespective of that, force will be always passing through what, those 2 point charges. So the similar concept you would be able to see in gravitation chapter as well, the closest approach and all that stuff. But we know regardless, only attraction is possible, right? In gravitation you won't be having repulsion, so between any two masses you can have only attraction. So there the body will be attracted, and then here also the same case, like till initially it will be like approaching, and after some time it will be like what, separating from the mass. So there also they'll be asking closest approach. Here instead of like similar charges, if I would have keep minus q, then it would have completely become like what, the gravitation question. So the same concept or the same similar model you can also find in what, gravitation. If you understand the concept over here, even the gravitation questions also easily you can tackle. So here whatever the role that electrostatic force is playing, there the gravitational force will also play the what, same role. Okay, and rest all the kinematic part is like what, same, the force, the velocity, the like all the stuff, whatever the process that I'm going to follow here, the rest remains what, same. But only thing is here in electrostatics both attraction and repulsion is possible, but whereas in gravitation only attraction is possible, right? So fine. So here the most important thing is, as force is always going to pass through the line joining both charges, net torque about fixed charge, as charge is passing through them, net charge about the fixed charge is 0. Whenever net charge is 0, we know we can conserve what, we can conserve angular momentum, right? So here you need to understand, but net force is not 0. Sir, how you are telling net force is not 0? It's an action reaction pair. No sir, yeah, it's action reaction pair, but the other charge is fixed, right? Someone is holding that charge, without like moving it, otherwise this charge would also get repelled, right? So if it is also like free to move, then what to do, that we'll discuss in along with the next concept, that is with the reduced mass. For time being it is fixed. Sir, how it will be fixed? Someone is holding it, right? Someone is applying some external force and holding it. That means here the key point that you need to understand is F net. Net force is not equal to 0. Net force is not equal to 0. That means externally someone is like ensuring that the second charge is fixed. That means no momentum conservation. No momentum conservation. No momentum conservation. Okay sir, understood. So because net force on the system is non-zero, so we cannot use momentum conservation. Yes sir, this is fine, momentum conservation. But what about torque? So as I said, net torque equal to 0. Net torque equal to 0 about what? About fixed charge. About fixed charge. So therefore what we can do, L is conserved. L means angular momentum. Okay, L is conserved. Okay sir, angular momentum is conserved. Fine. So then what about one more thing? See, like as there are no non-conservative force, okay, as there are no non-conservative force, as there are no non-conservative forces, energy must be conserved. Then you might be thinking about, sir, what about the external force that is there? So we are having an external force. Okay, what will happen to that external force? Yes, external force is there, but the work done by the external force is 0. Sir, how can you assure that work done by external force is 0? Why? Because this point charge is not at all moving, right? This point charge is fixed. Even though there is external force which is not allowing this to move, that is not going to do any work. Why it is not going to do any work, sir? Why? Because the displacement of this particle is 0. So work done by external force is 0. So and only force that is there is electrostatic force, which is conservative in nature. So therefore energy should be conserved. Initial total energy equal to what? Final total energy. That means, so as there are no non-conservative forces, we like energy must be what? Conserved. So as there are two unknowns, to solve two unknowns we need two equations, right? You can clearly see that what are the two equations. As I already told, momentum cannot be conserved. That means I had what? I had the condition for net torque equal to 0 and another condition for what? Energy should be conserved. By using these two I can easily find the answer or not. So let me use the angular momentum conservation. angular momentum conservation. Angular momentum conservation is nothing but what? R bar plus P bar, or simply I can write M into R perpendicular into V. So that means, see, the first equation that I am writing is initial momentum equal to final momentum. Initial momentum equal to final momentum. So what is initial momentum? mv naught into d. mv naught into d. So what is the final momentum? r minimum into what? V. So this is my equation number 1. From angular momentum conservation, you can see this is already r perpendicular to the v, so m into r perpendicular into v is the final angular momentum. So what is the initial angular momentum? Initial angular momentum, so this is the velocity and this is the what? R bar. So you need to take r perpendicular to the velocity. R perpendicular to the velocity is nothing but what? D. So m into d into v naught. M into r perpendicular into v naught. Let me just change it. M into d into what? M into r perpendicular into what? Velocity. So here I got one equation, right? So this is nothing but angular momentum conservation. Next, energy conservation, right? Initially they told it is at a very far distance, right? That means initial kinetic energy plus ke initial plus pe initial must be equal to ke final plus pe final. Final kinetic energy plus final potential energy. Sir, what is initial kinetic energy? Initial kinetic energy value, I know it is nothing but what? Half m v naught square. Half m v naught square. Sir, what about the initial potential energy? Initial potential energy is nothing but as it is at very far distance, so initial potential energy will be what? 0. And sir, what about final kinetic energy? Half m v square. Half m v square. Yes sir. Then what about the final potential energy? Final potential energy will be kq square by distance between them is what? R minimum. So you guys can see there are two unknowns, that is, what is one unknown? V, and another unknown is what? R minimum. And we got two equations. By solving these two equations, as we have only two unknowns, you can find the value of R minimum, right? So I hope this concept is also clear to you. And the next question that I am going to discuss is like the same question, but now I'll just ensure that this is also free to move. Then we'll try to analyze what will happen. So yeah, so I'll try to do that question in a different video. So that's all for this video. I hope you understood these two concepts. These both are like very important concept. So in multiple chapters these things can be used. Whatever the concept that I told earlier, that filling, defilling and symmetry, it will be this concept. Okay, this concept will be used in many chapters like rotation motion, center of mass, okay, rotation motion, center of mass, gravitation, electrostatics, all these chapters. Okay, and also this similar concept whatever I told, it can also be used in what? Gravitation. So both the models and both the concepts are very important. So yeah, so the next next class I'll come up with an concept of what? Reduced mass. Sorry I couldn't discuss in this video because it's already like more than half an hour, so I want to keep it in a different video. So because if I make lengthy videos, okay, so obviously your concentration levels of going through that entire video will be less, right? So that's why I thought of doing it in like same video. I thought it wouldn't take this much time to explain these questions, but I'm ensuring that the concept or like the analysis is delivered proper way, so that you will understand the complete scenario what happens. Okay, so if I want to solve this question, I would directly write these equations, right? So but that is not at all my intention. I want you to like make you understand each and every step, each and like every scenario what happens and what you need to do, how you need to like approach, and how you need to like do your thought process, keep your thought process, ensuring that solving these type of questions, and how to tackle when these type of models are given in different types of questions. So that is my motto. So it's taking long, right? So yeah, so even though if I said that I'll be doing reduced mass in this video, it's fine. So I'm doing like one more video now. So in that, so you guys can like go through what is that concept of reduced mass, and then as I said the same question, I'll take it up where this charge is also like what? Free to move, and then we'll see what happens. Okay, so I hope it's clear to you whatever the things that we discussed. Okay, thank you, bye bye.